All right, we've gotten through all the requisite theory, a couple of light demos. It's time to start writing code. Let's build our own word vectors. So you have a couple of options. You can follow along by going to github.com/thedeeplearners/TensorFlow live lessons, as I have here. And you can find your way into the notebooks directory. And we will be building this, creating word vectors with word2vec notebook. Now, the other option is to build it yourself interactively or run through it interactively within Jupyter Notebooks following our installation instructions earlier. So I'm going to be building this notebook for you guys. We're going to call it Word Vectors Demo. And we're going to give it a title. So creating word vectors with word2vec. I pressed 1 to create a markdown title cell, and then I'm pressing Shift-Enter to execute the line, which for the markdown just creates a nice looking title. And then I'm going to press I'm going to press Escape and M to create a little markdown box here. And you can just write something about what we're doing. So we're creating word vectors is what we're doing. Great. And so at the very top of the notebook, we're going to be loading our dependencies. So let's create a little subtitle. I'm pressing Escape and then 4 to create the subtitle. So we're going to load dependencies. So the first bit of code that we're going to execute is importing the natural language toolkit. From the natural language toolkit, which is full of useful natural language processing functions, we're going to specifically import the word tokenize and the sentence tokenize functions. We are also going to import gensim, and gensim is the package that is going to be doing our word2vec work. So we're going to import the word2vec algorithm from that. And we're also going to be using something from the scikit-learn package called tsni. I'll explain what that is later on. And we're also going to import pandas for working with data frames. We're going to import some functions from the Bokeh library for some fun interactive visualizations of our vector spaces. So we need to import these plotting functions as well. And we want all of our plots to show up in the Jupyter Notebook inline, so we'll add this little Jupyter Notebook magic. All right, so from NLTK, we're going to download a English sentence tokenizer. So this will enable us to convert the raw text into tokens, so into the words and the other elements that make up the natural language. And you can't just do that on like periods manually, because not all periods end sentences, and not all sentences, for example, start with capital letters. So you need something that's a bit more clever than that, and they Punkt, the German dictionary companies, provided a data set for doing that. Then we need to load our data. So we can download with the NLTK library, we can download the Gutenberg dataset, which consists of 18 different books, and we will have a look at what each of those are in a sec. So you need to download and then separately import the data. And then we can have a look at all of the various texts that are in there. So we have Jane Austen's Emma and Sense and Sensibility. We have the Bible. We have a bunch of Blake poems, Lewis Carroll's Alice, Moby Dick, and some Shakespeare as well. all in all, that is, yep, 18 texts. So the first thing that we need to do with our raw data is tokenize it. So we'll tokenize our text. We'll create a variable name, so Gutenberg sentence tokens, and to do that we will use the sentence tokenizing function on the Gutenberg raw data. So you can use this raw method to see the raw data if you feel like it. And then the tokens end up looking like this. So it has created lists. And it doesn't seem to have, with the default settings, done a very good job with new line characters, for example. So let's try another method to get a better look at this. So let's look at an individual sentence here. So that looks, yeah, I mean, it looks, this is definitely a sentence, so it did a good job of sentence tokenizing, but yeah, the new line characters are still in there, and we can use the word tokenize function to break that sentence down into individual words, as well as other punctuation marks. Now, that is a separate sublist now. So you could, for example, call out any given word from this list by running that tokenized function on all the sentences. So we pick that second sentence and pick the 15th word in it, and that's the word father. So you can see how this all pulls together. Now, those are the kind of manual functions for doing it, but conveniently, there is a method that exists a lot of the time on the corpi from the Project Gutenberg corpuses. So we can run this sense method on it, and that conveniently creates this list, which does handle the new line characters properly. So here you can see it's broken up the sentences into separate lists. Emma Woodhouse, handsome, clever, and rich, etc. And just as before, we can have a look at any individual one of those sentences. So you can see it's a list of words. So it did the sentence and the word tokenizing in one shot with that sense method on the Gutenberg object. And we can further, probe down to that word level if we want to get to the same word as before, father. Another convenient method that we don't immediately need is if you want to not have nested lists, so a list of words within a list of sentences, you could use the Gutenberg words method itself, which then just creates a single list of words. And you could use that, for example, to find out how many words are in our corpus here. So 2.6 million. All right, so now we've explored our data a little bit. Let's run word2vec on it. So the model looks like this. So we're going to create a model object, which will be a word2vec object. And it consists of, we need to specify what sentences we're feeding into it. So those are the Gutenberg sentences list that we created above. We need to specify how many dimensions we're going to have. So I did a lot of diagrams of three-dimensional, n-dimensional spaces. We talked about n-dimensional spaces with hundreds or thousands. For this application, with the amount of data that we have, 64 dimensions should be more than sufficient. We're going to use the skipgrams algorithm, which is not the default, but because it's a small data set, the skipgram should be fine and should work well with the rare words that we have in this smaller corpus. And as I described earlier, the kind of default window size that you can try out as a starting point with skipgrams is a window size of 10. So that means we'll have 20 context words 10 to the right and 10 to the left of any given target word. And we only want to run the word2vec algorithm on words that appear at least 5 times in our corpus. We're going to set a seed of 42, just for the sake of replicability. And you can set however many workers you want. That's how many cores on your machine you want to have dedicated to this task. This particular machine I have has 12 cores, and so I'm very happy to dedicate 8 of those to this task. Now, I have already run this model in advance so that we don't have to spend time watching this model run. And I saved the model with this model.save method, and I saved it as a file named raw Gutenberg model.word2vec. Now, so we can load that in. So let's explore that model. So the model is equal to gensim models word2vec load, and then we'll load in that word2vec object that I already created. So that was instantaneous. So let's have a look at word in the model. So let's pick the word dog. So here you can see the word dog is represented by 64 values, float values, that represent that dog's location in 64-dimensional space. And I can prove that to you that there's 64 here. You probably trust me, but there you go. Now you can see for sure. And there are some fun convenience methods that we can call in this model object. So we can see what are the most similar words to dog in this 64-dimensional space. Well, puppy is the most similar word. So it seems like we did a pretty good job training this. That makes a lot of sense. And then let's have a look at a few other much more abstract words like think. So the words that appear to be most closely related to think, so that have the shortest distance to it in our 64-dimensional space, are suppose, manage, know. That seems pretty good for this small corpus. I'm happy with that. And we can see pretty concretely with words like day, that morning, night, month, these are all similar kinds of concepts to day, so that makes perfect sense. Let's look at one last one here, because then we're going to riff on it and do some other exploration. So the most similar word to father is mother by a considerable margin, to then brother and sister, wife, etc. And we end up with some specific names. I don't know if these are from the Bible or Shakespeare works or whatever. From our corpus, of course, all of these word vector coordinates are directly a function of the corpus that we trained on. So there's another convenience method here that's kind of fun we can work with. We can look at, okay, of these terms, mother, father, daughter, and dog, which does not belong, which doesn't match? Well, clearly it's dog, so that agrees with us. And we can see, so mother and father are very similar. Father and daughter are quite similar. Now the distance from father to dog you can see the similarity, they're a lot less closely related. So we can also do arithmetic. So in our examples earlier, we talked about king minus man plus woman equals queen. Well, let's have another crack at that kind of calculation. So for the terms in our equation, the tokens in our equation that we want to have a positive valence, we put them in a list after the positive parameter, and then the ones that we want to have a negative valence, we give the negative parameter. So this equation here is father minus man plus woman. Where do we end up in our space? We end up at daughter. Now that probably isn't the right answer. The right answer would be mother, but we're not far off. And given this small corpus, mother being the third pick by a pretty small margin, that's reasonably reassuring. And so we can do this same kind of arithmetic with various kinds of terms. So if we change father to son, where do we end up at? So we have son minus man plus woman, we end up at daughter. Well, that's perfect. That's exactly what we'd hope for. And then I think we actually end up with some famous daughter names from the Bible here as the kind of next options. So that makes a lot of sense. And then we'll go through one more family example here. What happens if we change son to husband? We end up at wife. So that's perfect as well. Husband minus man plus woman should equal wife. And we're probably stretching the data here a bit, but let's try the canonical example. Let's try king minus man plus woman. What do we get? Well, it's not in any of the top 10, queen. Let's have a look a little bit further. Let's look in the top 30. There it is, queen, buried there. So in a much larger corpus, we would get the right answer here, probably. The words king and queen probably didn't show up too many times across our just 18 books. So we have a 64-dimensional space. It'd be nice to be able to have a look at it with our eyes, but of course, it'd be tedious to try to visualize a 64-dimensional space. So let's reduce our word vector dimensionality. And we'll do that with a method called tsne, which is t-distributed stochastic neighbor embedding. Now, what that allows us to do is it allows us to convert each of the words in our vocabulary from our 64-dimensional space into a much smaller one, whatever we specify. So how many words do we have in our vocabulary? Well, we can look at it with this little lookup. So we have 17,000 words. So there were 17,000 words that occurred at least 5 times each in our corpus of 18 documents. And we're going to create a variable that captures for each of those words in our vocabulary the location in 64 dimensions. And then we can use tsne to reduce that. So we're going to create an instance of a tsne object here. And we want it to have 2 components so that we can easily visualize it on a flat page. And you can set a number of iterations to run for. 1,000 is the recommended default. The minimum is 200. So you can set that to whatever you like and leave it to run. This line will work, but it will take a little while to run, so I'm not going to run it in this demo. And then you can use this next line to convert that tsne object. Well, this is the line that actually runs. So this is the line that actually performs the fitting. So we can run this line above. And then in this line here, we run the fit transform method on the tsne object. And this 64-dimensional representation of all 17,000 words. But I'm not going to run that now in the interests of time. However, I have created instructions here for converting the 2-dimensional object into a neat little data frame that you can have a look at. So I'll write that code out here. So we're going to take that x2d object, and we're going to assign 2 columns to it, which we can call x and y for our 2 dimensions. And then we're going to also add a column representing the name of all of the tokens. So we get the names of the tokens from the keys of this vocabulary. And then you'd be able to use just a quick method like head to have a look at that data frame. But I have already stored it. I've done all these tsne calculations, and I have stored it with a toCSV call here. So I called it raw Gutenberg tsne.csv. And we're not worried about the index, so you can set that to false. And in the interest of time, I'm just going to load it in now. So the next step that we're going to do is we're going to visualize a 2D representation of word vectors. And I have this little line here for reading in the coords df data frame that I already created. So we're going to read in raw Gutenberg tsne.csv. All right, so there we go. Read it in. So we can have a look at it here. There it is. So for each of the tokens, and you can see that this is the tokens as they first occurred in the data. So you can see a few more of those words. Let's see 20 of them. For each of those words, we have a specific coordinate in two-dimensional space down from the 64 that we initially had. And let's create a little chart to see all 17,000 of those words. So this underline is just a placeholder so that we don't end up outputting any numeric things other than the plot itself. So we're going to call the plot .scatter method on this data frame, and we're going to set the x and the y values to the x and the y columns in our data frame. And we can set a figure size of 12 by 12, works well on my screen. Although I've zoomed in a bit here, so maybe I'll be on the safe side and do 8 by 8. The marker that we're going to output to screen for each of the points is just going to be a small dot of size 10. And we're going to add some translucency. So 1 would be a perfectly dark spot, and 0.2 means that we have some translucency. So there we go. So we can see all 17,000 words and their relative similarity represented by short distance. And as a little bonus extra thing, I also have some code here for creating a fun interactive bokeh plot so that we can explore the individual words, not just looking at these dots. So use this output notebook function to load in bokeh and output in line, and then we're going to create, just so we're not working with all 17,000, because I found that things moved a bit slowly with all 17,000 words, let's sample 5,000 of them. And then we'll use these bokeh functions that we imported above to create our plot. So plot width, the dimensions work different here, and so I was fooling around with it. These numbers should work well. Plot height, we'll make a square. So 600 by 600. And then we want to add to that plot text, and that text, the location, the x is going to be the x column of the subset data frame, and the y is going to be the y column, unsurprisingly, and then the text is going to be equal to the token column that we created above. And then we can use this show function to actually show it. So there we go. How cool is that? So now, so this is the same diagram as up here. So this was 17,000 tokens, words, represented in this two-dimensional space, down from the 64 dimensions that we created with word2vec. And now we can actually explore the words on this set of them here. So you can scroll in, and so over here, for example, we have a bunch of numbers, because numbers tend to do the same kind of thing in text. They just tend to have about the same kind of meaning. Here are a bunch of proper nouns. We have, these ones all start with a capital letter. So one of the problems here that becomes obvious right away is that we're treating words, whether they have a capital letter in the beginning or not, identically. You know, we're just including all of them in here, whereas we want to be considering typically if a word has a capital letter at the beginning or not, it means the same thing. So we should be converting everything to lowercase. And there are a lot of other natural language best processes that we could account for here. And so in our next notebook, we're going to go through natural language best processes and make this space even better.